All right, hello everybody. Welcome back to Math Background for Machine Learning. So at the end of last class, we were looking at an example proof. So figure the first thing we'll do today is finish up that example. And just to remind you, the point is to show you a more complicated example of a proof. So instead of just proving that, peanut butter and jelly implies a sandwich or something like that, this is an example of a real proof that you would see in a class like 601 or 701. It illustrates all of the basic features of the proofs that we've been going over, but it uses a whole bunch of extra facts, and it includes many more steps, and therefore the way that people would typically present it will skip a lot of steps or do multiple steps as one step in the derivation. So to help people follow along, I've gone ahead and uploaded a typed up version of this same proof. And so let's start just by reviewing the proof, the part of the proof that we've already gone over so far. So if you'll remember, what we're doing is we're looking at a linear discriminant, which is a type of classifier in machine learning. It's based on the equation for a line. So here's a line here, and the equation of this line is ax plus by plus k equals 0. And everything on one side, where ax plus by plus k is positive, gets classified as a positive example, and everything on the other side gets classified as a negative example. That's where ax plus by plus k is negative. And so you would think of the x and y coordinates in this plot as measured features of your example. For example, the length and width of the petal of a flower that you were trying to classify. And then over here would be one type of flower, and over here would be another type of flower. And so we added notation W for our weight vector that we're trying to learn. That's the parameters A, B, and K from this equation here. And U for a training example, which is the X and Y coordinates, and then a constant 1, so that when we write W dot U, that's the same as AX plus BY plus K. All right, so that's what we're trying to do. That's the type of thing we're trying to discover, and we're going to learn it from data, and in particular we're going to use what's called streaming data. That means that we have a sequence of examples coming in one at a time. Each example we observe the xy coordinates, and after we observe those we predict a label, either positive or negative, +1 or -1, and then we get to see whether we were right or not. We get to see the true label, and once we do that, once we've seen the true label, we're allowed to update our parameters in preparation for the next example, which we're going to have to classify. So the perceptron algorithm, we described it last time around, but briefly just to remind you, we're going to start by initializing our weight vector to the vector of all zeros. So that means A, B, and K are all 0. And as long as we predict correctly, we're going to leave our parameters unchanged, so WT plus 1 equals WT. And then whenever we make a mistake, we're going to update our parameters. And the way we update our parameters depends on whether we made a false positive mistake or a false negative mistake. So if we should have predicted positive, but we actually predicted negative, that's a false negative, what we're going to do is we're going to add the training example UT to our parameter vector W. And the other way around, if we should have predicted negative, so we made a false positive, we're going to subtract the example from our parameter vector to get our updated parameter vector. All right, and we mentioned last time around that this rule kind of makes sense because if you add the example to the parameter vector, that means that if you see that same example again, W dot U will be larger. And then if you subtract it, W dot U will be smaller. And so that means you're more likely to classify it positively in the case of a positive example, and you're more likely to classify it negatively in the case of a negative example. All right. So the thing we're trying to prove is called a mistake bound. what the mistake bound is, loosely, is if there's an optimal parameter vector that we'll call W star that can classify all of our examples correctly, then we'll make at most some bounded number of mistakes before we find an optimal parameter vector. Won't necessarily be the same one. There might be many optimal parameter vectors, but we'll find one of them before we make too many mistakes. And in particular, I've written out the actual number that we're going to prove later, and it's here. So the assumptions we're going to make, so we assumed that there was a W star that classified everything correctly. That means that there's some lower bound epsilon bigger than 0, such that W star dot UT is bigger than epsilon for all positive examples, and it's less than minus epsilon for all negative examples. So it's bounded away from 0. We're also going to want to assume that all of our examples are bounded. So there's a constant capital U that upper bounds the norm of our examples. And so both of those are, I guess they're slightly stronger than just the assumption that there's an optimal parameter vector W, but they're certainly not that much stronger, and these are precisely the assumptions that we're going to make for our proof. And from these assumptions, we're going to prove this conclusion. And so, for example, if all of our examples are bounded to have norm no more than 2, if our parameter vector has norm 3, and if this epsilon here is a half, then if you just work this out, it turns out that we can make no more than 144 mistakes before we get an optimal parameter vector. All right, and in many cases we might make a lot fewer than that, but that's an upper bound. All right, so let's see. So in contrast to Wednesday, I've explicitly given a name to this parameter epsilon. On Wednesday's version of the proof, we were assuming that epsilon was 1, which you can do without loss of generality, but I think it's clearer if we actually give it a name. And let's see, because we hadn't used this assumption yet, the assumption of boundedness, I didn't write out that assumption on Wednesday, so this is new compared to what I wrote down on Wednesday. And so we'll continue reviewing the part of the proof that I went over on Wednesday, and then I'll let you know when we're moving to the new part of the proof that's going to conclude it, hopefully not too far into today's lecture. All right, so we started with what I've written here as part 1, and part 1 is going to show a lower bound on WT.W star. So WT is our parameter vector on the tth iteration just before classifying example T, and W star is the optimal parameter vector that we assumed to exist. So the way we're going to prove this lower bound is by induction on the time step. So after we're going to WT.W star starts at 0 because W1 is 0. And so 0 dot anything is 0. And so we're going to start with this, this quantity equal to 0. And then if we don't make a mistake, then the quantity is unchanged, right? We don't change our parameter vector, and so its dot product with W star also doesn't change. And so to complete the induction, all we have to do is look at what happens when we make a mistake. And there's 2 types of mistake we can make, so we'll go over each one of them at once. So if we make a mistake on a positive example, right, we update WT plus 1 is WT plus UT. And so WT plus 1 dot W star is this, WT dot W star plus UT dot W star. And UT dot W star, by assumption, that's at least epsilon, because we know that W star classifies UT correctly. All right, and so this is bigger than or equal to that plus epsilon. Same thing on a negative example. So on a negative example, we update WT plus 1 is WT minus UT. And so here we know that UT.W star is less than or equal to minus epsilon, because again, we assumed that W star classifies everything correctly. And so again, we get that WT plus 1 dot W star is bigger than WT.W star plus epsilon. And so that means after m mistakes, wt.w star has to be greater than or equal to epsilon times m, because we start at 0 and increase by at least epsilon on every mistake. All right. So that's the part of the proof that we went over on this past Wednesday, lower bound on wt.w star. So there's one more part that's about that complicated, and then we'll just put everything together and get the conclusion we want. All right. And as always, please feel free to ask questions to the TAs or on Piazza, and we'll try and answer them. All right. So here's part 2 of the proof. So here, before we were lower bounding something, now we're going to upper bound something. We're going to upper bound the norm of the parameter vector. That should be subscript t, not superscript t. I'll fix that after lecture, sorry. So after a mistake on a positive example, again, the norm of wt doesn't change if we don't make a mistake, because wt doesn't change unless we make a mistake. So in order to figure out the lower bound, we're going to again prove it by induction, and we're going to look at how wt is updated in case we make a mistake. So here, in the case of a mistake on a positive example, wt plus 1 is wt plus ut, and so wt plus 1 squared, right, the dot product with itself, we just expand the square, we get wt.wt plus 2wt.ut plus ut.ut, right? This is the standard just algebraic way of expanding a square. And then we can look at each one of these terms separately. So wt.wt, that we're leaving unchanged. ut.ut, we assumed that, so this is the norm of ut squared. And so we assumed the norm of ut was bounded by capital U, and so that's less than or equal to u squared. And then here, we assumed that we made a mistake, right? And so that means that we classified this example ut as negative, which means that wt.ut is less than 0. And so we can replace that by 0, and we get that here the quantity on the t plus first time step is the quantity on the t time step plus u squared, or less. It's at most that much. All right, and it should come as no surprise that something like this is also going to be true for negative examples. So here, when we complete the square, right, we're updating on a negative example. If we make a mistake, we update wt plus 1 to wt minus ut. And so we complete the square and we get wt.wt minus 2wt.ut plus ut.ut. And the only thing that's different now is that we know that wt.ut is positive because we classified this example as positive. And so when we subtract it, we again have the subtracting a positive number is less than 0. And so we get the same bound on how much wt.wt changes. All right, and so just doing the induction, again, we start with the norm of our parameter vector at 0. We increase it by at most u squared on each mistake. And so after m mistakes, we get that it's at most m times u squared. And a little bit of rearranging, basically take the square root, so this is the norm squared, we'll take the square root, so we get that the norm is bounded by u times the square root of m. All right, so that is the perceptron proof part 2. And then part 3 is just a little bit of algebra, right? So from part 1, let's scroll back up to part 1, right? So we have wt.w star is bigger than or equal to epsilon m. And so rearranging that a little bit, that's m is less than wt.w star over epsilon. All right, and by Holder's inequality, the dot product between two things is less than the product of their norms, less than or equal to. So we can replace wt.w star by the norm of wt times the norm of w star. And then we bounded the norm of wt before, right? So here's the bound on the norm of wt from part 2 of the proof. So we can just substitute that in and get this, right? And now we can rearrange a bit. We divide through by the square root of m and then square both sides, and we get this expression. And that was the expression that I promised that we were going to prove. So by basically examining how two quantities can change. One is the dot product of our weights with the W star, and the other is the norm of our weight vector. By comparing how those can change over time, we showed a mistake bound for the perceptron algorithm. All right, so to recap, the point of showing you this proof is to show you a real-world example of a proof that you might see if you went on and took further machine learning courses. And so we've gone through this proof in a little bit more detail than we would go through it if we were teaching 601 or 701. And hopefully that gives everybody some practice with following a proof. If you had trouble following the proof, please ask questions on Piazza. You might expect, for example, that there might be a homework assignment, like let's say a short, one of the short problem sets coming up, where you would have to go through a proof like this one and explain what was going on, the same way I just explained it in lecture. All right. And in fact, you can, if you like, download from the lecture notes site. So here is a PDF version of the same proof that I just went through. And so if we go all the way to the end, right, we can see that this statement here, right, this is the conclusion of the proof. And this statement follows from that statement, right? And all we did was algebra, right? Now, if we wanted to be if we wanted to be more detailed, we could say specifically that we divided through by the square root of m and squared both sides. You know, depending on your audience, you might want to say the justification at either one of those levels of detail, right? And then this one, right, it followed from two things. It followed from that one, and it also required that one, right? And it required basically to substitute this into this, right? And so that's an example of how you would go through and mark up a proof to make sure you understand it, right? You would go through and you would look for all of the separate statements in the proof, all of the separate claims in the proof, and for each one, you would mark it as following from some previous ones by some inference rule, right? So like algebra, that's a vague description of the inference rule, but it's fine for this purpose. Or you could go through and mark something as an assumption, right? So here, right, that is an assumption. Right? And you can tell, right, it's marked by English that says it's an assumption. It says it's marked by suppose, right, which is a word that we use for assumptions. And so if you completely analyze a proof, you'll get to the point where your tree of little arrows bottoms out in assumptions, right? Every leaf is an assumption, and then every internal node is something that we derived by one or more steps from the assumptions that we've made. All right, so that is the that's the process of understanding a proof, and hopefully you guys all are able to follow that. And if not, please ask questions on the on Piazza or in office hours. All right. Let's see. So in particular, I'm going to hand out an assignment today. I'll post it right after class, or in one if we take a break during the class later today. And the assignment is going to be precisely to finish the process that I just started. So take a copy of the perceptron.pdf, which is available from the schedule page on Piazza, and to mark it up to show what's an assumption, what follows from previous statements, and by what process of inference. So just a warning that an assignment, this will count as a short problem set, and it's going to be due on Friday, and it'll be out during or after lecture today. All right. As a matter of fact, why don't I think it would be a good idea for me to post that, let people take a look at it, and I'll just wait 5 minutes to see if people have questions. So give me a second. I will just, all right. All right, the assignment is now published on Canvas, so you guys should all be able to click over to it and download it. I'll just pause for 5 minutes to let people take a look at it, start trying to do it, and ask me any questions on Piazza in case there are things that are difficult to understand. So we'll be back in a few minutes. All right, so we're back. We've answered a few questions on Piazza, so please continue asking more questions, and we'll do our best to answer those as well. But I wanted to go back and continue going over our lecture notes because I'd like to get done with the lecture notes on logic today, and hopefully move on to the next topic, which is probability. All right, so far we've looked at a logical system called propositional logic, or more precisely, we've looked at constructive and classical propositional logic. And there's a ton of other logical systems as well. And so, propositional logic is a good example because it's a fairly simple system. It's one that's familiar to a lot of people, and it's the basis for a lot of more complicated systems. But I wanted to give you a sense of at least a couple of other important logical systems. So the first one is first-order logic. So first-order logic extends propositional logic with a new data type, a new class of thing called an object. So an object is something like a person, or a course at CMU, or a tuple in a database. The point of an object is to sort of store a bunch of related propositions and reason about them together. So for example, we could have an object named Socrates, representing the ancient Greek philosopher. And you could have a bunch of properties of that object. You could know whether Socrates was a man, you could know whether he was mortal, you could know whether he was Greek, you could know whether he was Roman, right? And there's a whole list of things you could know about him. And so, up till now, if we wanted to reason about whether Socrates was a man, we would have had to introduce a separate proposition called something like man underscore Socrates, right? And there would be no a priori relationship between that and mortal underscore Socrates, right? Like we would have to have separate propositional variables for each thing we wanted to reason about. Here we have an object, Socrates, and it groups together a bunch of related properties. So, for example, the ancient Greek philosopher was in fact a man, he was in fact mortal, he was in fact Greek, and he was not Roman. And so these sort of structured propositions, you can still work with them through all of the propositional logic connectives, things like and, or, implies, not, that sort of thing. And once you introduce these properties that an object can have, then every time you introduce another object, let's say Caesar, it will also have its own copy of each one of these properties. So Caesar will know whether Caesar was a man, whether he was mortal, whether he's Greek or Roman, and so forth. And so the properties have the same names, but they have potentially different values. So Caesar, in fact, was Roman and not Greek. And so we think of these these properties, man, mortal, Greek, Roman. We think of them as functions that take in an object, Socrates or Caesar, and return a truth value, right? So if we write, U is equal to the set of all objects, right? Meaning all objects that could potentially exist in our world, so there's infinitely many objects that could potentially exist, but maybe only, some finite number that we're actually talking about. Then a property, right, also called a predicate. That's the same as an element of the set U to true or false, right? So it takes an object and it returns a Boolean value. And so this here, right, this arrow is representing a function type. So we've used now two different meanings for the arrow. It can either be the implies symbol in propositional logic, or it can be, it can represent a function type. Here it's representing a function type. And so just like we can have single argument predicates, we can also have, two argument predicates. So that would be a function from u cross u to a Boolean value, t comma f, right? And we can also have, unsurprisingly, three argument predicates and so forth, right? And so an example of a two argument predicate is right here. Right, here's a predicate friends that takes two arguments, Socrates and Plato, and let's say Socrates and Plato are friends, and so this will return true. All right. So first order logic, in addition to having objects and predicates, it introduces these things called functions. So functions in first order logic are a specific type of function. In particular, a function is an element of U. It's specifically a function that takes an object and maps it to another object, or takes a pair of objects and maps it to an object. Right, that's U cross U. And then the same thing, we can have three argument functions as well. And so forth, right? So predicates and functions look similar. They both take objects or tuples of objects as arguments, but a predicate returns a Boolean value, true or false, and a function returns another object. Right? And functions let us say something like, we can say something like the advisor of Plato was Socrates, which happens to actually be the case. Plato was a student of Socrates. And we can ask, was the advisor of Plato Greek, right? So we can have a function returning an object that then gets passed as an argument to a predicate. So we could ask, for example, whether Socrates was friends with the instructor of 10606, and unfortunately, no, I never met Socrates and never had a chance to become friends with him. All right, so why have we introduced all of this extra complexity? The reason for it is basically to let us reason about many different propositions all at once. So instead of reasoning separately about mortal of Socrates, mortal of Caesar, mortal of Plato, right, we can reason about all of them at once. So we might say that, for example, for any object x, if x is a man, then x is mortal. Right? That seems like a reasonable thing to be true. And first order logic, I haven't described how, but it will let you reason about these statements that have a variable in them, right? We don't know yet which object they're referring to. And so we're going to say something about all possible objects at once. And so to achieve this benefit, first order logic has a richer set of inference rules than propositional logic. So it upgrades, the familiar rules like modus ponens or De Morgan's laws or whatever to take account of objects. And then it also adds additional rules that don't make sense in propositional logic. So an example of one of those rules is something called the Rule of Substitution. And again, I'm not going to give that rule in full detail, but it basically says that if you have something that's true for all dogs, then it's going to be true as well for all German Shepherds, which are because all German Shepherds are dogs. And so it lets you take a variable which ranges over some class of objects and replace it by a variable that ranges over a smaller class, a subset of that class of objects. And anything that was true for the larger statement is true after restricting the variable to go in a smaller class. All right, so that's a whirlwind tour of first order logic. We're not trying to give a complete introduction to first order logic because you would have to take if you wanted like a full introduction to all different types of logic, there would be an entire course that you would take for that. But the point is to just illustrate that there is another, useful example of a reasoning system, and it looks a little bit different from propositional logic, but the proofs have the same basic structure. In particular, always a proof in first-order logic will start from a set of assumptions, and it will proceed to introduce new statements and justify those statements in terms of previously proven statements, including our assumptions. And every time that justification, either it's an assumption or the justification is via an inference rule. So another example would be a logic with what's called a logic with a theory. So a theory is basically a set of rules for reasoning about a given type of object. So real numbers or sets or integers or functions, that sort of thing. So the way we do that is we'll start with our existing logic and we'll throw in some new objects, some new predicates, some new functions, some new facts, and possibly some new inference rules for reasoning about these things. So for example, we might have a theory of real numbers that introduces objects for all of the real numbers, things like 1.4 or pi. Functions for working with real numbers, so plus, times, squared, that sort of thing. And facts about these objects, things like 0 is a real number, or the sum of any two real numbers is a real number. And once we've done this, once we've introduced this theory of the reals, we can make a proof. And that proof is going to start from assumptions or from known facts. And it will justify each one of the new statements. It will add new statements and justify each one of them as following from some previous statements via an inference rule. And though there may be new inference rules in this case, so in a theory of the reals, we might, for example, have an inference rule that lets us do linear combinations of known equations. So I have an example of that here, right? We have, suppose we know these two equations. There's an inference rule that lets us take twice this equation and subtract it from that one, and we would get x equals 1 as the output of that inference rule. All right, so that is that's two good examples of additional logics. And again, the point of mentioning them is not necessarily to give you a complete idea of what's included in each one of these examples, but just to show you that there are many different logical formalisms that we can use, and they're designed for reasoning about different types of thing, or for expressing different types of reasoning. And in all of them, they'll all have this notion of proof, and the proof will always be a sequence of statements, each one of which is justified by an inference rule from previous statements. And you can do things like introducing lemmas, right, or dividing up your proof into digestible chunks, right? The rules for talking about a proof are the same in each one of these. All right. So, so one last thing that I want to do with logic before we leave that topic, and that is to go over an interesting example. So we left that example. We didn't discuss it specifically in the lecture when we went past it, but I wanted to go through and work on it a little bit in order to again, give people a little bit more practice. So this is an example of pure propositional logic, and it's just a slightly more complicated example than the ones we've seen so far. So I don't know how many of you have played the game Sudoku, right? You can find Sudokus on the internet or in newspapers for those of you who actually ever pick up a piece of, paper newspaper. The point of a Sudoku is to reason logically to fill in a grid. So you'll have a grid like this one. It'll start with some numbers already filled in, right? So here we have, it's a 4x4 grid. Full-size Sudokus, it's a 9x9 grid, but we'll do a mini Sudoku, which is a 4x4 grid. Every cell is either blank or starts with a number in it. And there are some constraints about how you can fill in numbers. So in particular, in every row, like that, of 4 squares, in every column of 4 squares, and in every heavily outlined box of 4 squares, the digits 1 through 4 each appear exactly once. Right? So for example, here, because there's a 1 in this group of 4 squares, there can't be a 1 in any one of these other squares. And the key thing about Sudoku puzzles is that the ones that they give you, guessing is never required. So they fill in enough digits so that if you reason cleverly enough, you can always 100% of the time back out exactly which digit has to be in which blank square. And so what I've done here is I've marked 4 of the blank squares with letters A, B, C, and D. And our goal is to fill in the puzzle and figure out what the squares A, B, C, and D are. And so what I'm going to do, I'm going to pause briefly and let you guys try and fill that out. And we'll be back momentarily. All right, so we are back. So hopefully you guys enjoyed the little puzzle. I just made a copy of the puzzle here, and I'm just going to go through and fill it out just so that you can see what the process looks like. So first we know, let's take the digit 3 to start out with. So we know there's a 3 somewhere in this group of 4 squares. We know it can't be in those 2 because there's only one 3 in that row. We know it can't be, there's only one 3 in this column, so it can't be in those 2 squares. So we've eliminated that square, and that square, so we know there has to be a 3 there. All right? Then Same thing for a 2, right? So we know there's a 2 in one of these 3 remaining squares, and it can't be either of those 2 because there's a 2 above them in the same column. So the 2 has to be, there's only one spot for the 2, and it's there. Then the 1 can't be here, so it has to be here. And then there's only one remaining digit, 4, so it has to be there, right? So that's how you would solve the mini Sudoku. And then the next thing that would be interesting is, okay, so that's the process of reasoning. You can do it, in your head, but how would we do it using propositional logic? And the way we would do that is we would take each one of our assumptions, meaning the rules of the game, and translate it into a propositional logic formula that we would assume. And then we would reason about the conclusions that we could draw from those assumptions. So for example, we could use, so these squares A, B, C, and D, we could write variables that mean something. So we could write, for example, A1 to mean the proposition that there is a 1 in cell A, right? And then similarly A2 up to A4, and then similarly the same thing for B1 to B4. That would give us the contents of cell B, right? So, and C1 through C4 and D1 through D4, right? So those would be the propositions that we would work with. And then we could introduce formulas that look like, well, so for example, there has to be a 1 somewhere in this quadrant. So we could write A1 or, there has to be, could be in cell A or cell B or cell C or cell D, right? And so we know that this formula has to hold, right? That's an assumption that we're making because it's stated here in English as being part of the rules of the game. Same thing, let's see. You could check, for example, you know that here's a digit 2, so there can't be a 2 in B or D. So we know that not B2, and we know not D2, right? And so you could go through and write out all of the knowledge that you have from the game. Sometimes some bit of English language text might take several formulas to write out. So let's see if there's an example of that. Oh yes, so here this shows that the formula has to, this formula shows that 1 has to appear in at least one of the cells A through D. We should also be able to write that it appears in at most one of the cells, right? So to write that out, we know that it is not the case that there is a 1 in cell A and a 1 in cell B, right? And we know that it is not the case that there is a 1 in cell A and a 1 in cell C, right? And so forth. There's going to be, for choose 2 is 6 different formulas, right? That eliminates all of the possibilities of there being a 1 simultaneously in 2 different cells, right? So it takes just one formula of this form to say that there's at least one in the group of 4 cells. And if we want to limit ourselves to simple formulas, it takes 4 more to write that constraint. We could, of course, write it all as one big formula, but then it would be a complicated one. All right. So might be a good idea to continue, on your own writing out what these logical formulas are, and to use that as practice for proofs. For example, when I've written it out like this, the resolution inference rule is going to be particularly particularly useful, right? So I can know, for example, that there's a 3 in at least one of these squares. So I'll write out a formula A3 or B3 or C3 or D3. Actually, let's go ahead and write that out. A3 or B3 or C3 or D3, right? And then from this guy we know not A3 and not B3. And from this one we know not B3, I'm not going to write it down again, and not D3, right? And so if we use resolution on this guy and this guy, right, these guys will together give us B3 or C3 or D3, right? And then we can resolve from this one and that one and get C3 or D3. And then finally, from this one and that one, we resolve the D3 with the not D3 and we get just C3. Oops, that's messier even than my usual handwriting. C3, right? And so now from these assumptions, right, here's an assumption, here's an assumption, here's an assumption, here's an assumption, we get this conclusion. Okay, so that's an example of using logical reasoning on a slightly more complicated propositional logic example. All right, so we should just have time now. Again, keep asking questions on Piazza, but we should just have time now to start looking at probability. All right, so probability is for reasoning about things that we can't predict exactly, which is most things. And so probability lets us say for events that might happen or might not, how likely do we think they are to happen? And we're doing it now because we've just done set theory and logic, and probability builds very nicely on set theory and logic. Okay. We'll start with a universe or a sample space that we'll call capital S. These are a set of what we'll call atomic events. So atomic means that it can't be divided further. So this is like the simplest possible event that we're going to consider. So an example of a set of atomic events would be if we're talking about rolling a die. There are 6 possible die rolls, 1 through 6, and so our sample space would be just the integers 1 through 6. Then for each one of these atomic events, we can assign a probability. So those probabilities are non-negative and they sum to 1. 0 means that the event is possible, 1 means that the event is certain, and in most cases we're somewhere between that, and we're going to reason about things that might or might not happen. All right, so those are atomic events. From the probabilities of the atomic events, we can reason about compound events. So a compound event is a subset of the sample space. So we'll write E for a compound event, and E is a subset of S. And the probability of an event E is just the sum over all atomic events that make it up of the probability of that atomic event. So for example, a compound event might be the event that we roll an even number, and that corresponds to the set of 2, 4, and 6. Those are the even die rolls. If we say that each one of the die rolls has a probability of 1 over 6, then the probability of rolling an even number is a half, which is a sixth plus a sixth plus a sixth. And so you can see here why set theory is nice, right? We can write out events using set builder notation, or we can use set operations to talk about the relationships among multiple events. And we can also describe them using logic, right? Like we can say some property holds and some other property holds. And there's a nice correspondence with that as well, right? Like set operations correspond to logic operations in the sense that if we ask for a number that is both even and a multiple of 3, right? That's the same as intersecting the sets of even numbers with the sets of numbers that are multiples of 3, right? So intersect 2, 4, 6 with 3, 6. And just another little bit of notation. So sometimes instead of an explicit and, we'll just write a comma. So in set builder notation, you've already seen that, right? You'll list out a set of properties that all have to hold for an element to be included in the set. Same thing with a probability, right? We'll write probability of event A, comma, event B to mean the probability that both of them happen at once. In other words, the probability of A and B if you're thinking of them as logical expressions, or A intersect B if you're thinking of them as sets. All right, so we can use Venn diagrams to help us visualize probabilities. A Venn diagram is basically like a big rectangle where we write small circles or other shapes inside that rectangle to represent the sets or events that we're reasoning about. So the probability, if we write, here's our universe, capital S, this square, here's our event, an event A, right, is everything inside here. Points inside the big square are our atomic events. The atomic events in which A is true are inside this circle, and then the ones that are inside the square but not the circle are the worlds in which A is false. So we think of our atomic events as possible worlds, and we think of our compound events as sets of possible worlds, or properties that could hold in our possible worlds. A lot of times we'll try to make the areas proportional to the probability of the event, but a lot of times when we're making a Venn diagram, we might not know ahead of time what that probability is going to be, and so we won't be able to make the probabilities proportional. All right, so an experiment. So we can use probabilities now to describe an experiment, right? So an experiment is something that we're thinking about. We do something and then we measure something, right? So we might roll a die and measure the number of spots on top of that die, or we might go stand on a corner, let's say Forbes and Craig, and administer a survey to the next person who passes by, and then that experiment would result in observations that are equal to the answers that that person gives to the survey questions, right? And so a lot of times when we think about an experiment, we actually have to think about a fairly large set of atomic events, right? If we have 10 true-false questions on our survey, then the person might answer each one of them true or false, or yes or no, and there are 1,024 possible sets of answers that the person might give. Even more than that, they might decide not to answer some of the questions, so there's 3 to the 10 possible surveys we could get from the next person who walks by. So we can write out a complicated sample space, a complicated universe, using a tree like this one, right? So at the beginning we have no knowledge, and then we flip one coin and we know what its outcome is, heads or tails. And then after that first one, we'll flip another coin and know its outcome, heads or tails, right? Or we could start with an empty survey and fill out the first question, and then the second, and then the third, and so forth. All right, and so the leaves of this tree are our sample space, so 2 heads, heads, tails, tails, heads, or tails, tails. And here we've assigned probability of 4th to each one of these, which is equivalent to the assumption that the coin is fair. Right. And so when we conduct an experiment, we might measure exactly the atomic event that we reach. So we might know that we got a heads and then a tails. Or it might make sense to talk about an experiment where we don't observe the difference between some subsets of our sample space. So we might have the experiment of counting the total number of heads instead of observing, was the first coin heads, was the second coin heads, right? And if we only count the total number of heads, that corresponds to an experiment that splits our sample space into 2 heads, 2 tails, and 1 head and 1 tail. And the 1 head and 1 tail option has 2 possible atomic events in it. Right? So anytime that you're describing probabilities, it's important to think about what is our universe, what's our sample space, and what is the experiment we're doing, meaning what events might we observe within our sample space. So far most of our examples have been uniform distributions, and that's a pretty common way to think about it. But distributions don't have to be uniform, right? We can assign different probabilities to each one of our atomic events, and then that those get added together to give the probability of each one of our compound events. For example, we could have a non-fair die or a non-fair coin. All right, so there are a lot of useful rules for working with probabilities, and the point of this section is to remind you of those rules and give you practice with working with all of those rules. So let's see, we probably have time to get through at least a couple of them. So one of the rules that's useful is called disjoint union. So if we have a Venn diagram where there's an event A and an event B and they don't overlap, meaning that the probability of A intersect B is 0, then the probability of A or B, right, which is A union B, is just the probability of A plus the probability of B. And you can figure that out using the definition of the probability of a compound event, right? So the probability of A is just the sum of all of the atomic events inside A. The probability of B is just the sum of all of the atomic events inside B, and the probability of either of them, meaning A union B, is the sum of all of those atomic events, either in A or in B. And so we know that because they are not overlapping, we're not counting anything twice if we just add the probability of A to the probability of B. All right, and disjoint union works for more than one set at a time, so that's useful. All right, non-disjoint union is a little bit more complicated. So if we have two events A and B that are not mutually exclusive, meaning that there's an overlap here in the Venn diagram, the probability of A union B, we can calculate it by splitting the Venn diagram into 4 pieces, right? So there's the part that is neither an A and B, and then for A union B, there's 3 pieces. There's A minus B, this red part here, B minus A, which is this blue part here, and then the overlap is purple, that's A intersect B, right? So P of A union B is P of A minus B plus P of B minus A plus the intersection. All right? So in particular, these 3 things are disjoint, right? So P of A is P of A minus B plus P of A intersect B, right? This part, the red plus the purple part. And P of B is the blue part plus the purple part, right? P of B minus A plus P of A intersect B. So we can write P of A plus P of B is going to be the sum of these 2 things. So it's P of A minus B plus P of B minus A plus twice the probability of A intersect B, right? Because we counted A intersect B in the probability of A, and we also counted it in the probability of B, right? And so we can rearrange this. We get P of A plus P of B minus P of A intersect B is equal to P of A union B, right? And so this is just the union rule, right? You can express the probability of A union B, decompose it that way. And then there's an intersection rule, which is just a small rearrangement away. P of A intersect B is P of A plus P of B minus P of A union B, right? And so either one of these is a useful inference rule to use when working about probabilities of sets. All right. So let's do one last rule before we close for today. So that is the sum rule, which is that if you take an event A, here this ellipse here, you can split A into 2 disjoint events using any other compound event B. So you can split it into A and B and A and not B, right? So here, right, in this overlap is A and B, and this part that's not overlapping is A and not B. And we know that the probability of A, because these 2 things are disjoint, the probability of A is equal to the probability of A and B plus the probability of A and not B. Okay, and that's the sum rule. And it's quite useful, particularly in its version where we split into several mutually exclusive and exhaustive parts, right? So if we have that B1, B2, B3 are mutually exclusive, meaning that their pairwise intersections are all 0, and if they cover B, right, B is the union of B1 through B3, let's say, then the probability of A is the sum over all of these possible sub-events, BI, of the probability of A and BI. Right? So that's the sum rule. All right, and I think that is probably a pretty good place to stop. My office hours start now. As a reminder, to attend office hours, you can either knock on my door. I'm in Gates Hillman Center, 8105, or you can message me on Google Hangouts, and my my Google ID for doing that is available on Piazza. So is my office location, I think. And so, yeah, I'll see you guys next time around. Feel free to keep asking questions on Piazza or in office hours. And good luck with the exercises. See you later.